Hello, my name is Alfonso Lanuza. I'm a student at Dominic Schneebel's group at Stony Brook University. And this is my talk for the March meeting 2020. I'm going to talk about how to simulate spontaneous emission by using an optical lattice, an external microwave, and ultra-cold rubidium atoms. This is our system. The rubidium atom can be in a red internal state that fills a very deep optical lattice and be trapped within one of the lattice sites. When this happens, you can think of the lattice site as being a quantum emitter in the excited state. Now, because of the action of the external microwave, the internal state of the atom can radio-oscillate into a blue state that fills the optical lattice much more weakly. When this happens, the rubidium atom can abandon the lattice site in the form of a Bloch wave, and you can think of it as being radiation emitted by the quantum emitter. It's because of this that the system obeys a Weisskopf-Wigner type of Hamiltonian. This type of Hamiltonian was proposed to describe spontaneous emission. However, many of the phenomenology that it predicts was just too difficult to achieve experimentally. In a previous work published by my group, we show that this phenomena can be achieved with our system. This includes non-Markovian decay, emission spectra, and time-of-flight pictures of the bound state. In that work, we focused in the simplest scenario of having only one quantum emitter and no blue lattice. The objective of this talk is to introduce the theory that goes beyond this simple case. To solve the dynamics, one just needs to expand the atom's wave function in the basis of red and blue states and solve the Schrödinger equation via Laplace transform. The subsequent inverse Laplace transform might look imposing, but it can be solved as any other complex path integrals by using the residue theorem, as we will see next. In the previous scenario, the inverse Laplace transform has some simple poles and a branch cut. When the microwave detuning is highly non-resonant with the parabolic dispersion relation of the blue state, the emission is suppressed and the rubidium atom remains bound to the emitter. Then the dynamics are dominated by this simple pole. When the detuning is resonant with the bottom of the parabola, the dynamics are dominated by the branch cut, and the non-Markovian decay takes over. And if we keep increasing the detuning until it is highly resonant with the parabola, new poles appear. The one with negative imaginary part dominates the system, and it represents exponential decay, the decay rate being the imaginary part of the pole. The conjugate pole also exists, but it lies beyond the branch cut and it doesn't have any physical implications as it escapes the integration contour. If it did, it would yield to an exponential increase of the population instead of a decay. But how does this change if we now have a lattice for the blue states? New band gaps appear in the dispersion relation for these states, and these affect the dynamics. In particular, new branch cuts appear as they are always located at the band edges. Also, new bound states appear. These bound states can live within the band gaps, and the beating between each other can lead to oscillations in the asymptotic population of the emitter. Once you know the dynamics of the red piece, the blue piece can be obtained by direct integration of the Schrödinger equation. The result looks like this when you scan over the microwave detunings. This can also be understood by elementary physical principles. By energy conservation, the radiated piece must conserve the energy of the emitter. This means that the radiation distribution is centered at the dispersion relation. Since this plot is taken at a finite pulse time, Heisenberg uncertainty principle results into an uncertainty in energy equivalent to this uncertainty in lattice momenta. This equation also implies a remarkably simple formula for the bound state distribution in lattice momentum. This has a single peak for bound state energies below the band and two peaks for bound state energies within the first band gap. And the beautiful thing about all of this is that we have experimental evidence of all of it, of the decay dynamics, the bound states, and the emission spectrum. Finally, let's see what happens when you populate all of your lattice sites. When you consider all of the emitters, you recover translational symmetry in your system, which implies that the Fourier transform decouples the dynamics. If you look at the inverse Laplace transform for one of these Fourier modes only, all the singularities that would yield to decay now are gone. And this makes sense because your quantum emitters are all over the place, so you cannot really escape them. However, you are left with an infinite set of simple poles, and they correspond with a new energy band structure. This new band structure is the polariton band structure. So if this is your detuning, and these are your blue energy bands, they hybridize into these polariton energy bands in purple. And a very few simple properties that you can prove for these polariton bands is that the lowest one is always lower than the detuning. All other polariton bands are sandwiched between two blue energy bands, and the higher polariton bands are very close to the blue energy bands, even though they don't cross them. These polariton bands almost don't contribute to the dynamics. Future experiments might shed some light on this polariton case. These are our references. When you have no blue lattice, this is the experimental paper, and this is the theory paper here. When you have a blue lattice, the theory is still in preparation, but the experiment is already on the archive. And when you have infinite emitters, my lab mates are still having ongoing measurements. Thank you.